All right, so our last section of 15.2, line integrals. So we're going to talk about the differential form of line integrals. And the differential form will come up in our next section, and it's just another common way that you'll see line integrals expressed. So part of what we're doing is trying to get you familiar with the different representations of line integrals, and the other part is we're introducing this notation because it's very common for what we're going to do with line integrals in the next section. And I was looking through the rest of the chapter. We get to do such cool stuff for the rest of the chapter. This is really my favorite. This was always my favorite part of the calculus sequence, was when we get to this part of calculus. We get to on Monday we'll talk about another kind of facet of the fundamental theorem of calculus. And then finally at the end, I keep saying at the end of the unit, we're going to bring all this stuff together, and we'll talk about what the divergence means and what the curl means, and bring it all together. But each of those things is another kind of piece of a bigger idea of what the fundamental theorem of calculus is telling us. So we're coming kind of full circle all the way back to this thing that we learned in Calculus 1 about the fundamental theorem of calculus, kind of putting it under a bigger umbrella, making all of these things that we're talking about in this chapter part of a bigger idea of what the fundamental theorem of calculus is telling us. So it's really, I think it's really cool. I was looking over and I was really excited that we get to do it again this year. All right, so just a quick summary of what we've done with line integrals so far. So we have a line integral of we talked about the line integral of a scalar field. Whoops. So we had a scalar field f. And our line integral was on a curve our curve was C, the line integral was the integral along C, and we notated that as f of xy ds, and we figured out that we evaluate this by parameterizing the curve. We express f in terms of our parameterization. And ds turns into the length of r prime dt. So we parameterize our curve in terms of t, express f in terms of the parameterization, and then we evaluate this integral. So that was our line integral for a scalar field. For a vector field, we wanted the line integral of our vector field, and we said that the line integral along our curve of C was f, our notation was f dot dr, and we said that was, we wrote that in several ways. That was the integral along our curve of f dot t ds, where t was a unit tangent vector. And the way we evaluate that was we evaluate the integral from a to b. We represent our vector field in terms of our parameterization. And we took the dot product of that with r prime. And took the integral with respect to t. So that's how we evaluated our line integral of a vector field. what we want to do, what we're going to do today, is find a connection, find a relationship between this and this, between these two forms. And again, it's another common way of representing line integrals, and we'll use that form in our next section. So let's find this relationship between this and this. Because in the end, when we evaluate this integral, we get a scalar, and when we evaluate this integral, we get a scalar. So each one is a scalar, and they're kind of a similar thing. So let's figure out how they're related. Let's connect the two of these. So what we're going to do is, and we'll do the argument in the plane, and the extension to more higher dimensions is just a simple adding coordinates. So we're going to say that we're going to use a notation that our vector, and we talked about this before, f of xy is m I plus nj. We talked about this when we were talking about conservative fields and talking about the curl. And we're going to say our curve is parameterized by r of t, and that's x of ti plus y of tj. So this is how we're going to express our curve and our vector field. So f dot r prime, in this case, which is part of our integrand when we integrate, when we do a line integral of a vector field, f dot r prime turns out to be m times dx dt plus n times dy dt. When we take our dot product. And then our integral, so when we do our line integral, the integral of along c of f dot dr is going to be the integral along our curve of m dx dt plus n dy dt times dt, and that just simplifies to the integral along our curve of m dx plus n dy. And if we have x, y, and z, this extends. We just have our extra component and our dz component here. So this is our representation of the line integral of this vector field. Normally, we write this, we leave out the parentheses, and we just write the integral over c of m dx plus n dy. So here's our connection between the integral of a vector field, the line integral of a vector field, and line integral of a scalar field. We started off with a line integral of a vector field. It turns out that the line integral of the vector field is the sum of these two line integrals of these scalar fields. Because m is just a scalar function, and n is just a scalar function. So our line integral of our vector field turns into the sum of these two line integrals of scalar fields. So this is our connection. Couple of important notes. Now, and the reason that we're doing this is this representation. This is called the differential form of the line integral. This representation is important for what we're going to do as we move forward in the chapter talking about line integrals. We'll see this representation quite a bit. Questions before we go on? We'll do some examples of how we use this representation to evaluate our line integrals. So a couple of important notes. The value, it's important to remember that the value of a line integral is independent of the parameterization. So the other day, Caitlin, you asked about, there was a piecewise smooth curve, and the book had parameterized it differently than you had. And I said it didn't matter how you parameterized it. No matter how we parameterize the curve, when we evaluate the line integral, that line integral will come out the same no matter how we parameterize. Because the parameterized curve, we express our vector field or a scalar field in terms of the parameterized curve. That's going to affect the limits of integration. So no matter how we parameterize our curve, we get the same value. The other important thing to remember is, now that we're talking about line integrals of vector fields, the orientation of the curve affects the sign of the line integral of a vector field. So it affects the sign of the integral of f dot dr, and it affects, and by extension, this would affect the sign of the integral of our differential form, m dx plus n dy plus p dz. It does not, the orientation does not change the integral of our scalar field. And what we're saying is, just to be more specific, that the integral of negative c, and what I mean by negative c is we're going the opposite direction of f dot dr, is the negative of the integral going around the other direction with the opposite orientation of f dot dr. So when we change the direction of our, if we parameterize the curve in the opposite direction, we change the sign of the integral for a line integral of a vector field. And the reason it changes the sign is when we parameterize our curve in the opposite direction, our unit tangent vector points in the opposite direction. So it changes the direction of the unit tangent vector. It doesn't change the sign of the line integral of a scalar field. If we think about the line integral I mentioned when we talked about it, we could think of that as the area of the fence that's above our curve. Taking our integral in the opposite direction doesn't change the area of that fence. But when we use a vector, changing the orientation changes the direction of the unit tangent vector. Any questions on this so far? All right, let's look at a couple of examples of using the differential form to evaluate some line integrals. So we want to, for this example, we want to find f dot dr for f equals x squared y I plus x y to the 3/2 j. And our curve is given by r of t equals t plus 1I plus t squared j. 0 less than or equal to t less than or equal to 2. And we're going to use the differential form for our, we're going to take a look at how to use the differential form to evaluate this integral. So we said that the integral along our path of f dot dr was the integral along our path of m dx plus n dy. Do I have an extra parentheses there? I do. No? No? Okay. All right, so for this representation, m is x squared y, and n is x y to the 3/2. And for our curve, on our curve x equals t plus 1, so dt equals what? Or I'm sorry, dx. dx equals dt. This is like a u sub. dx is just dt. And y equals t squared. So dy equals 2t dt. And then I just plug in m and dx and n and dy and evaluate my integral. I have my limits on t here. So my integral of f dot dr is going to be the integral from 0 to 2 of m, which is x squared y, times dx, which is dt. And let's see, x squared y, I need to substitute. Sorry, I jumped in too soon. X squared y. So x is, so I get t plus 1 squared. And y is t squared. Times dx, which is dt. Plus x y to the 3/2. So I get t plus 1 times t squared to the 3/2, which is just t to the 3rd, times dy, which is 2t dt. So that's my integrand. And when I evaluate that, this is an easy evaluation. We just have polynomials. So this comes out to 256 over 5. So all we did here was, it's very similar to what we did before. We picked out our components of our vector field, represented those in terms of our parameterization, and also represented dx and dy in terms of our parameterized curve, and evaluated the integral that way. We could have done our dot product, represented f in terms of our parameterization, done our dot product, and done it that way. Turns out to be the same thing. So I just want to do a couple of examples of using this differential form to evaluate our line integrals, because we're going to see that a little more often as we move forward. Questions? All right, let me look. So what we're going to do next is we're going to use the same field, and we're going to evaluate this integral on using a different path. So our first path was t plus 1I plus t squared j. So we're going to use the same field on a different path. So same field. On C, which is given by R of t equals 1 plus 2 cosine ti plus 4 cosine squared tj. And 0 less than or equal to t less than or equal to pi halves. So on our field, or on our curve, sorry, on C, x equals 1 plus 2 cosine t. So dx equals what? Minus 2 sine t dt. And y equals, excuse me, 4 cosine squared t. So dy is minus 8 cosine t sine t dt. So now we can substitute in to our equation. We're going to use our differential form. The integral of c of m dx plus n dy equals, and I'm going to represent this time x and y in terms of our parameterized curve. So that's going to equal the integral from 0 to pi halves. 0 to pi halves of 1 plus 2 cosine t squared times 4 cosine squared t dt, plus for my y part I get 1 plus 2 cosine t times, this turns out to be a little long, times 8 cosine to the third t. I'm just substituting in for x and y here. 8 cosine third t times negative 8. I need more room. Negative 8 cosine t sine t dt. So we have a long integral here. But we just have powers of sine and cosine. When I evaluate this, I'm not going to go through the evaluation. When I evaluate this, I get negative 256 over 5. How does that compare to the first one? Negative. It's opposite. So why did that happen? So we had our this curve. This curve is parameterized in terms of sine and cosine, and t equals t is 0 to pi halves. In my first orientation, I represented r as t plus 1 and t squared j, and t goes from 0 to 2. So any ideas what might have happened here? No? All right, let's take a look. So Emily says same path but different orientation. So let's take a look at our starting and end points. On the first curve, r of 0 gives me 1, 0. And we went from 0 to 2. R of 2 is the 0.34. And on the second curve, r of 0 is 3.4, and r of pi over 2 is 1, 0. And if we would compare those curves, the parameterizations of those curves, they would be the same curve. We're going in the opposite direction. So that's what changed the sign. So even though the parameterization was different, it was very different, we went in the opposite direction, and we got the opposite sign integrals. All right, I just want to do one more example, and then we'll be done for today. This is kind of like one of the homework questions we asked about today. We want to evaluate the integral along C of 2x minus y dx plus x plus 3y dy, and C is the arc on x or y equals x to the 3 halves from the point 0, 0 to 4, 8. So we already have our line integral expressed in differential form. We could rewrite this as a vector and evaluate our line integral using our procedure for line integrals of vector fields. But since it's already in this differential form, we're gonna use our differential form. So m, I'm going to say that in this case, our m is 2x minus y, and our n is x plus 3y. And for this, what do we want our parameter to be on our curve? We need to parameterize this curve. You could say x equals t. Let's see, 4 to the 3 halves. So on C, we're going to let x equal t and y equals t to the 3 halves. So dx equals dt, and dy equals 3 halves t to the 1/2 dt. And now we're just going to, now we're going to plug in, we're going to represent, represent these in terms of, represent m and n in terms of x and y, and substitute into our expression for our integral. So the integral that we have, the integral from t equals, if x equals t, t is going to go from 0 to 4. And we have 2x minus y, so that's 2t minus t to the 3/2 times dx, which is dt, plus, and here we have x plus 3y, so we have t plus 3t to the 3/2 times dy, which is 3/2 t to the 1/2 dt. And we end up with just polynomials to integrate here. So this is an easy integral to evaluate. When we evaluate this, we get 592 over 5. So same kind of procedure. We want to represent x and y in terms of our parameter, represent our dx and dy in terms of our parameter, and substitute in and evaluate our integral. I don't want to do another example. I just want to ask a question about an approach. So let's say we wanted to find the lateral surface area over this curve x squared plus y squared equals 4 under x squared minus y squared So here's our problem. We want to find the lateral surface area over this curve and under this function. So what is this problem asking us to do? What would be our procedure? First off, what is the curve? X squared plus y squared equals 4. So it wants the lateral surface area over this circle under x squared minus y squared equals 4. So if we think of thinking back what we did with multiple integration, f of x, y, what's another way we could express f of x, y? How can we think of that? What do you guys think? All right. The question is, all right, we know this is a circle, so we want the lateral surface area above this circle and under f of x, y equals x squared minus y squared equals 4. So thinking back, oh, I'm sorry, this shouldn't be equals 4, this should be plus 4. Thinking back to what we did with multiple integration, if the problem asks us to find the volume find the volume over a region bounded by f of xy equals x squared minus y squared plus 4, what is this function telling us? And what f of xy, what variable does this represent? Z. So we could think of this as z equals x squared minus y squared minus 4, or plus 4, sorry. So what is z equals x squared minus y squared plus 4? What kind of thing? I'm not worried about the shape, but what, relative to the xy plane, what is z? If the xy plane is here, which direction does z take us? Up. So this is, what this question is asking us is to find on this curve, this is the height. We can think of z as the height above the curve. This is our height above the curve.
X. Y.
This is the height above our curve. So if I'm just going to draw a rough picture here, if this is my xy, if this is my coordinate system, and we have this circle in the xyz, or in the xy plane, this is some surface above this circle.
So can we just do it from the x-axis up?
And what we're looking for
That's a parabola.
is,
It's a parabola thing? It's a plane.
I think this is a hyperbolic paraboloid, I think.
That's difficult.
But we don't, that doesn't matter. It doesn't matter what it is. All right, stick with me, guys. This is asking us to find the surface area above this circle, below this surface. So the lateral surface area. So we have this side, and at the top here, it's wavy somehow or other, and we want to find the area of the sides. So if this is the height, if this is our height function, if we want to think of it that way, and this is our curve, how do we find the total height around this curve that's below this surface?
We do the integral of the z, and then the bounds are c. The bound is the circle.
So we're going to do the integral. I'm going to try to make sure I'm going to translate what you said. So we're going to integrate z, right? We're going to integrate x squared minus y squared plus 4 and what's our integral over? What kind of integral is this going to be?
Double integral. Triple integral.
Yeah, what is it, Charlie? This is the line integral
Line integral.
of c of our function ds. This is our height. So we want this function, we want the sum of the height of this function around the path. So this question is asking us to find the line integral of f of xy ds over the curve. That's what this question is asking us. There are some homework problems that are like this, so I wanted you to understand what on the quiz. I am not sure if one of these, if I put one of these
Please don't.
like this.
That is so mean.
But so all this is asking us is to do this. This is the line integral of f of xy ds.
Okay.
This is not hard. It's just translating what the question is asking us.
So then this is when you use the magnitude of r prime.
Magnitude of r prime, yes. So this is the very first one we talked about.
Right.
All right. That was painful. All right, your homework. I'm not sure.
I think it's probably really helpful like in college towns.
Yeah, that's what I was thinking too.
Yeah, it gets Brazil.
Because
Think
what?
about the Brazilians.
Yeah, and my people in Europe, and because my thought was to take them down and start reposting,
Right.
but maybe I'll just take like as I post the new one,
Yeah.
take the old one down. Because I also have over 3,000 views now,
Wow.
and I want to keep
The other
that
day
number.
You only had 1,000.
I have like 3,200 now or something.